Question 7 is coming from circular measure. The diagram shows a metal plate ABCDEF consisting of 5 parts. The parts BCD and DEF are semicircles. The part BAFO is a sector of the circle with center O and radius 20 centimeters, and D lies on this circle. The parts OBD and ODF are triangles. These ones here. Okay, angles BOD and DOF are both theta in radians. Part A, given that theta is equal to 1.2, find the area of the metal plate. Give your answer correct to 3 significant figures. Now, you should know that in here, the calculator must be in radians. We know that area of the sector, because for us to get the area of the metal plate, we shall need the area of this sector OABF, or okay, ABF or OBAF, this sector here. Then we shall need to add the area of this semicircle, then this one here, and the area of this triangle and that triangle there. So the area of the sector is given by a half r squared theta. But where does it come from? It comes from here. Theta, the angle subtended by the arc at the center of the circle, then divide by 360 degrees, because the angle sum in the circle is 360 degrees. And since the sector is part of the region enclosed by the circle, then we multiply by the area of the circle, which is pi r squared. But in radians, this 360 is actually 2 pi. Okay, then times this pi r squared. So this one can go, and then you can see that you get a half, then r squared theta. Okay, the same thing that happens to when we come to length of an arc. Okay, length of arc is equal to r theta. Remember, it is also theta out of 360, and an arc is part of the circumference of a circle, and the circumference of a circle is given by 2 pi r. Remember, 360 is 2 pi, so times this 2 pi r, automatically this 2 pi and this one, they will disappear. Then you remain with this one here. So that's where these formulae come from. Okay, so in circular measure, you need to know these two, and also where a triangle is not right angled, then think about using the sine rule and the cosine rule. Okay, so if the triangle is right angled, then you can use the SOHCAHTOA and then the Pythagoras theorem. So that is that. Now let's go. They want the area of the plate. Now, to get the area of the plate, remember we need to get the this one here, the area of this, and this one, the semicircles. Okay, but this length here, we know this length, and the angle in between. So to find it, we can use cosine rule. Okay, or I can divide it into 2, and then I can also find it that way. So using cosine rule, let's begin using cosine rule. I will have BD, which is actually equal to DF. That will be the square root of this one squared plus this one squared, 20 squared plus 20 squared, then minus 2 times 20 times 20, then cosine of the angle which is opposite to this side, which is the theta here, and that is 1.2. Okay, so simplified, I can have it as, this is 400 plus 400, that will be 800. Then minus, this one is also 800. So 800, then cosine of 1.2. So I can leave it there. So that means, of course, now that is going to be the diameter. So what will then be the radius? So radius of the semicircles, is going to be, which semicircles, by the way? BCD, and this one is DEF, and DEF. This one is going to be a half of what we get out of here. So a half of the square root of 800 minus 800 cosine of 1.2. I'm going to leave it there exact, okay? I'll round off at the end of it all. So we are going to now get the area of the plate. Area of the plate is going to be equal to area of this major sector, area of major sector, OBAF. Okay, this one here, OBAF, this sector here. I've called it major because there is this minor here. Okay, all right. Then from there, we shall add, what are we adding? The area of these two triangles here, and they are congruent. They are equal, so I'm going to say 2 times area of, even the semicircles are the same. So 2 times area of semicircles, okay, let's say BCD, this semicircle here, BCD. So its area times 2, then it will give me this. It is actually, if you get 2 semicircles, it's the same as getting 1 a full circle. Then plus also area of triangle. The triangle, I can take OBD. So remember, I'm also multiplying it by 2. OBD. So this 2 here is multiplying those. Okay. Now, area of the major sector. Remember, we have area of the sector is a half, then r squared. So what is the radius of this major sector is 20, and then the angle is here, which is going to be 2 pi, that is 360, then minus 2 theta, okay? 2 pi minus 2 theta. So I'm actually going to put this one here like this, 2 pi minus 2 theta. All right. Now, we have the radius is 20 squared, and we have 2 pi, then minus 2 theta. Theta is given as 1.2. That will be the area of the major sector. Then we go here, 2 into. Now, area of the semicircle is a half. It is a half area of the circle, a half pi r squared. So what is the r? R is this one here. Okay? We got it here, a half of this one, that will be the radius. So we shall have a half of the 800 minus 800 cosine of 1.2. Remember, the calculator here must be in radians. This radius here is squared. Then plus area of a triangle, which is not right angled, is a half. You have something like this. You know the angle here. If this is A, this is B, and you know these 2 lengths, it is just a half, then times this side, which you know, times this other side, you know, then sine of the angle, which is in between them. Okay, as simple as that. So that is what I'm going to put here, and then I say that a half times, we have the 20, we know it, the 20, and then the angle here. Okay, so we shall have a half here times 20, then sine of the angle, which is 1.2, given there. Okay, and then from here, I can even do some simple simplification. This is 400 divided by 2, that will be 200, into 2 pi, then minus, this will be 2.4, then plus. So this times 2, that one will go, and then we shall have here pi, okay, into. Now, when I square here, this will be over 4. Now, of course, this square root will go with the square, okay? Now, 800 divide by 4, that one will give us 200, not so. So meaning here we have 200, then minus again 200, then cosine of 1.2, then plus again this 2 here times this one here, that one will go 20 times 20, that is 400, then the sine of 1.2. Now I put everything here in the calculator and then we see what we get. Okay, 200 into 2 pi. Now my calculator here is in degrees. Okay, so I need to first change it to radians. Shift mod, then rad is 4, then we have 200 into 2 pi minus 2.4, then we have pi into 200 minus 200, the cosine of 1.2, close that bracket, then close the bigger one, then plus 400 sine of 1.2. So we get 1550.095135. That is 1550.095135. Of course, to 3 significant figures, I'll just round this one off to this plus 0, so it will be 1550. Okay, centimeters squared. This is 3 significant figures. That is that. Part B, given instead that the area of each semicircle is 50 pi centimeters squared, find an exact perimeter of the metal plate. Now, area of the semicircle, first of all, area of semicircle, we know that it is equivalent to a half, then pi r squared. Now this one is equal to 50 pi. So pi will disappear, and then we shall have our r, which is going to be equivalent to the square root of 2 times the 50, that's 100. Okay, meaning we shall get 10 centimeters here. Now, that means BD is going to be equal to, let's go back here. Our BD is here. So we have gotten the radius, which is 10. So meaning BD is going to be 2 times the 10, that will be 20. Okay, so do you see that you are going to have 20 here, 20 here, and 20 here? So this one is an equilateral triangle, meaning now theta here is going to be 60 degrees, 60 degrees, 60 degrees. You see that? Okay, so let's go back. We shall say BD is now going to be equal to 2 times 10, which is equal to 20 centimeters. Okay, so meaning that triangle OBD we have seen is now an equilateral triangle. So therefore, theta is going to be equal to 60 degrees, which is pi over 3. Now we need to find the perimeter of the metal plate. So perimeter, remember for perimeter, we add the length around the given shape. Perimeter of the metal plate. This one is going to be equal to, let's go back and we check. We shall get length of arc BAF. Then we have this this circumference, half of the circumference of this, the semicircular arc, and also this one here. Okay, so we can go back and now we write that the perimeter of the plate is going to be equal to length of major arc BAF, then plus, I'll just say 2 times the length of arc BCD. Okay, BCD, because we have seen that this one here is the same. If you check here, if I get for BCD, it is the same as for this one. So I just get this one times 2. It is like actually the circumference of that circle, because if this is a half, the circumference and also half the circumference, don't you think you get one circle? Okay, so going back here, we shall then have length of the major arc. Remember, it is r theta. So the r is 20. The theta, we got 2 pi minus 2 theta. You remember? 2 pi minus 2 theta. Check here. This one here. And our theta is pi over 3. Okay. Then plus 2 times length of an arc is r theta. So we have seen that for the other semicircles, the radius is 10. Okay. So that 10 there, then times the theta. Of course, theta for this one, when you come to this one here, the theta is going to be 180. Okay, 180. In other words, it is half the circumference of the circle. As simple as that. So I'll have pi here. Then, now, do you see that this one gives us 2 pi r? The radius is 10, then 2 pi. Full circumference, because you have 2 arc lengths, which are just half the circumference of the circle. Now, let's multiply all through. This one will give us 40 pi, then minus. This one will also be 40 pi over 3, then plus 20 pi. Okay, then 3 times 40, that is 120, minus 40, that will be 80 over 3 of pi, then plus 20. Okay, now 3 times 20, that one is 60. Now 60 plus 80, that is 140. So we have 140 over 3 of pi. Okay, this will be in centimeters. That will be our perimeter. They told us exact. Yes, they said find the exact, so I can leave it there. Don't put it to 3 significant figures.